Welcome into the 8th week of the open course on diffusion in multi-component solids. This is the 33rd lecture in the series. In this lecture, we will discuss the theory of random walk of particles. We will show that root mean squared displacement of a large ensemble of particles making random walk is proportional to the square root of the number of jumps an average particle has made. So far, we have seen the significance and applicability of diffusivity term, which is defined as a phenomenological coefficient. In next two classes, we will try to understand the theoretical significance of this term diffusivity. The unit of diffusion coefficient is meter square per second. So, it indicates some kind of rate, specifically the rate at which the compositional front travels, but why the unit is meter square per second and not meter per second? We will get the answer in next two classes. Fick's law came into existence in 1855, but it was not until 1905 that the theoretical significance of this term diffusivity was established. It happened when Einstein developed the theory of random walk around 1905. Now, what is random walk to do with diffusion? So, let us first try to understand what is random walk. We know at any temperature above 0 Kelvin, atoms or molecules of a substance continuously undergo thermal motions. In solids, this thermal motion is in the form of vibrations. So, the atoms vibrate about their mean position continuously, and the energy of vibration keeps changing. If you talk about all the atoms, the way the available energy is distributed among all the atoms keeps changing continuously with time. In liquids and gases, the particles undergo translational motion. So, if you track any one particle, it is undergoing a translational motion. So, it is moving from one position to another until it collides with another particle. After the collision, the particle will change its direction and now would move in new direction. Now, this motion will occur again until the particle hits with another particle. Again, upon the collision, it will change its direction and this will continue. So, we say each particle is undergoing a random walk. So, if you consider a particle in a liquid or gas, if we track it, let us say it starts from a position A, it moves in a particular direction until it hits another particle. After the collision, it changes its direction of travel, moves in another direction until it again hits with another particle, then it changes its direction and this continues. And in some time t, the particle has made some net displacement. So, after let us say five such jumps, the particle has made a net displacement from A to B. Let us call this r bar. Now, obviously, the net displacement A B bar is the summation of all the displacement vectors corresponding to these individual jumps from 1 to 5. So, if a particle makes let us say n jumps and each jump vector is denoted as r I bar, then we can write r bar is equal to r 1 bar plus r 2 bar plus r 3 bar and so on. till r n bar. Now, if we consider an ensemble of particles which is located at x equal to 0 initially, each particle will undergo random walk and will make some net displacement in certain amount of time. So, the particles will randomly move in all directions randomly, and each jump of the particle or the each jump vector is random, which means each jump is independent of its previous jump in both direction and magnitude. So, if we track, because of this random walk, this particle distribution will slowly spread in space with time. Now, if we want to track how much this distribution has spread in certain amount of time, what is the right parameter that we should use? And one of the option is obviously the average displacement of all the atoms, and it is denoted as r bar in triangular bracket. So, r bar in triangular bracket denotes average of net displacements of all atoms. This is also referred to as net displacement of an average atom. Now, if the particles are undergoing truly random walk, then the average net displacement would be 0. If we look at this particle ensemble and if we track the front after a certain time, we would see this front is growing we will see that this distribution is spreading isotropically. That means, if you have a particle which has made a net displacement, let us say r I bar, there is a almost certain chance that there would be another particle which has made an equal and opposite net displacement, let us denote that r j bar, and they will cancel each other. And since we are dealing with a large number of particles, it would happen that the average net displacement will be 0. So, obviously, the average net displacement of all atoms is not a good parameter to work with. So, what is the right parameter that we should use? As we will see later, Einstein realized that it is the mean square displacement. Or MSD in short, and it will be denoted as r square inside triangular bracket. So, it is the average of squares of net displacements of all atoms. So, let us try to find out the expression for mean square displacement, r square inside triangular bracket. So, if we consider any one particle, we have the expression for r bar, which is given here, r bar equal to sigma r I bar I equal to 1 to n, if the particle has undergone, let us say, n jumps. So, for our particular particle, r square would be r bar dot r bar. So, which we can write as r1 bar plus r2 bar, r3 bar, and so on till rn bar dot r1 bar plus r2 bar plus r3 bar, and so on till rn bar. If we expand this, we get r1 bar dot r1 bar plus r1 bar dot r2 bar and so on till r1 bar dot rn bar. If we write last few terms, it will be r1 bar dot rn minus 2 bar plus r1 bar dot rn minus 1 bar plus r1 bar dot rn bar. Now, taking the dot product with r2 bar, will be r2 bar dot r1 bar plus r2 bar dot r2 bar so on till r2 bar dot rn minus 2 bar plus r2 bar dot rn minus 1 bar plus r2 bar dot rn bar plus taking the dot product with r3 bar. If I write all this term till dot products with rn bar, now we can simplify this expression by writing it in terms of summations. So, we can start with the diagonal terms. So, if we take all the diagonal terms, we see they are of the form ri bar dot ri bar so we can write r square equal to, and there are n such term. So, sigma ri square I goes from 1 to n. Now, let us consider the non-diagonal terms. We see this is a symmetric matrix about the diagonal. So, if you see the off diagonal terms, they are similar. So, r1 bar dot r2 bar is same as r2 bar dot r1 bar, r1 bar dot r3 bar is same as r3 bar dot r1 bar, and so on. So, we can just consider one side of the diagonal and just double it. Now, if we look at it row by row, r1 bar dot r2 bar plus r1 bar dot r3 bar and so on, we can write this as sigma r1 bar dot rj bar, and j is varying from 2 to n, multiply by 2. Similarly, the second row we can write as r2 bar dot rj bar, and j here is varying from 3 to n, so on till you have to multiply by factor of 2 here. Write last couple of terms, it should be rn minus 2 bar dot rj bar, and j here will be from n minus 1 to n, 2 times r n minus 1 bar dot rj bar, and j here will be from n to n. So, there will be only one term under this summation here. Now, if we further simplify this, if you write in terms of double summation of r I square from I equal to 1 to n plus 2 times double summation r I bar dot r j bar. I here is varying from 1 to n minus 1 and j you can see is varying from I plus 1 to n. So, we can write expression for r square as sigma r I square equal to 1 to n plus 2 times r I bar dot r j bar we can express as r I r j cos theta I j r I r j cos theta I j. I is from 1 to n minus 1 and j is from I plus 1 to n. R I r j are the magnitudes of the ith and jth jump vectors, and theta I j is the angle between ith and jth jump vector. So, if you look at this summation, what we are doing just is that we are considering each jump vector and taking its dot product with every jump vector that occurred after it. Right. So, if we consider an example, a particle making let us say just few number of jumps, let us call it r1 bar, r2 bar, r3 bar, r4 bar, r5 bar. This is r. So, here the particle has made 5 jumps, and if you want to evaluate this, let us call it r5 bar. R5 denotes the particle has made 5 jumps. This should be of course sigma r I square to 1 to 5 plus 2 times we have to take dot product of every jump vector with the jump vector that occurred after it. So, we will start from r1 bar dot r2 bar plus r1 bar dot r3 bar plus r1 bar dot r4 bar plus r1 bar dot r5 bar plus for 2 the r2 bar r3 bar plus r2 bar r4 bar plus r2 bar r5 bar plus r3 bar dot r4 bar plus r3 bar dot r5 bar, and for 4 will be r4 bar dot r5 bar. So, we need to know angle between each jump vector and every other jump vector that occurred after it, that is the cos theta I j. So, for example, cos theta 2 and 4 is the angle between r2 bar and r4 bar. So, if we extend this r2 bar and this is r4 bar. So, the angle between r2 bar and r4 bar is the cos theta is theta to 4, and we have to evaluate the cosine of the angle cos theta to 4. We have to do this for each all the pairs of the jump vectors. So, if we consider the case of solid, this expression becomes a little bit simpler, and the reason being in solids all the jump lengths are equal. So, in solids all jump lengths are equal, that is Ri equal to Rj equal to so on, let us call it lambda. So, if we write the expression for solids, this will be sigma Ri square n times lambda square plus Ri Rj, since all jump vectors are again same. So, this will be lambda square, which we can take out. So, 2 lambda square, this summation of cos theta I j, I varies from 1 to n minus 1 and j varies from I plus 1 to n. You can write, simplify this as m lambda square times 1 plus 2 by n Now, this is for one particle. We need the average of square of net displacements of all the particles, right. So, we need to evaluate r square inside the triangular bracket. Now, each particle has undergone n jumps. So, we denote more precisely this as r n square, r superscript n denotes that particle has made n jumps. So, if we try to evaluate this, we will get the expression as r n square average equal to n lambda square times 1 plus 2 by n average of cos theta I j and summed over I and j, I equal to 1 to n minus 1 and j equal to I plus 1 to n. Now, let us try to understand what is this average cos theta I j. So, what we do is we consider each pair of jump I and j, we consider this pair for each atom, evaluate cos theta I j for each atom and take the average of it. That is this average cos theta I j, and then we sum it over all I and j. Okay. So, in our previous example here, if I consider R1 bar and R5 bar, so I need to know theta 1 5 for one atom, then I evaluate cos theta 1 5 for second atom and so on for all the atoms and then take the average. That gives me average of cos theta 1 5, and we do this for every pair of the atom, and that is this average of cos theta I j. Now, this can further be simplified if we are considering a true random walk, that is the atom is free to jump randomly in the solid, then this summation should be 0, right. So, the cos theta I j should be 0 for true random walk. Why? Because here we are considering a large number of atoms. So, if we consider a pair of particular jumps I and j, for every Ri bar dot Rj bar that one atom has, there is almost a certain chance that you will find another atom which has made ith and jth jump such that its Ri bar dot Rj bar is exactly equal and opposite to the first atom, and they will cancel out each other, since we are considering large number of atoms and a truly random walk problem. So, let us try to understand this. For example, if we consider the jumps on 1 1 1 plane of an FCC crystal so let us say if we consider two atoms, atom 1 and atom 2, and if we consider ith and jth jump pair, this is atom 1 for example, if it makes a jump from site O to A as ith jump, which is let us say OA bar. For another atom, if this jump vector is OA bar and jth jump is to B, so let us call this AB bar. For another atom, and other jump vector is AC bar, and we see that OA bar dot AB bar should be equal to minus OA bar dot AC bar. In solids, angles between the jumps are restricted, right, because the coordination shell is fixed in a solid. So, the atoms can jump only on the particular sides, and in this particular FCC case we have seen this will be true for any pair of ith and jth jump, and so the average of cos theta ij would be 0 for true random walk. So, we can very simply write this expression Rn square mean square displacement MSD Rn square is equal to n lambda square, or if we write root mean square root Rn square average should be equal to root n lambda. This is important. What it tells me that the root mean square displacement is proportional to square root of the number of jumps and not to the number of jumps. And this is important because if we consider an individual particle, if it makes n jumps, it might have actually traveled a large total distance, but the net displacement will be much lower because the net displacement will be proportional to root n. Here we can consider a nice example which is given by Paul Schumann in his book. If we consider for example the problem of carburizing. Typically, the carburizing times employed are a few hours to obtain a case depth of few hundreds of microns, right. So, let us consider 3 hours of carburizing time, which is roughly about 10 to power 4 seconds, and each carbon atom makes about 10 to power 10 jumps per second. So, in 3 hours total number of jumps an average carbon atom will make n would be equal to 10 to power 4 times 10 to power 10 equal to 10 to power 14 jumps. Now, the jump distance in case of carbon is around 0.1 nanometer, which is 1 times 10 to power minus 10 meter. So, if we just wrongly consider that the root mean square displacement would be proportional to n, then the distance travelled in 3 hours by an average atom would be 10 to power minus 10 times 10 to power 14, which is 10 to power 4 meter, right, which is 10 kilometers. But typically we see the case depth that we get in 3 hours is about 600-700 microns, and the case depth is not the total distance or the total penetration of carbon atoms in the steel. So, it will be the total penetration would be larger than that, about 1 mm or so, and which will be clear from here, because the root mean square displacement is proportional to root n. So, we can write the RMS displacement of an average carbon atom would be square root of 10 to the power 14 times 10 to the power minus 10, which would be equal to 10 to the power minus 3 meter, which is around 1 millimeter, which is consistent with what we observe in practice. So, got an important result that the root mean square displacement is proportional to square root of the number of jumps that an average atom has made. Okay, so we will stop here. Thank you.